Welcome, students! In this explainer, we are going to break down one of the trickiest topics in your SPM chemistry paper, rusting. We're going to give you the tools and, more importantly, the thinking process to conquer pretty much any question the examiners decide to throw at you. Okay, but before we dive in, here's a pro tip. Just watching this is only half the battle. To really make this knowledge stick, you've got to put it into practice. So after you're done here, scan this code or head on over to MCQSPM.com. You can tackle some real past year questions there. Trust me, it's the best way to lock in what you're about to learn.
So, why are we focusing so much on rusting? I mean, it seems pretty simple, right? We see it on old gates, on cars, it's everywhere. But here's the thing, examiners absolutely love using this topic to set some really clever traps. It's one thing to know what rust is, but the real marks, the A+ marks, are in understanding the how and the why.
Right. So to beat the examiners at their own game, we need to go deeper than just, brown flaky stuff. We've got to understand what rust is at the atomic level. And it all starts with the fundamental chemistry behind it.
At its very core, rusting is just a redox reaction. Now, don't let that word scare you. Redox is just a mashup of reduction and oxidation. All it means is that we have a reaction where tiny particles called electrons are being passed around. One substance loses electrons, we call that oxidation. And another substance gains them, and that's reduction. That's it. That is the secret to the entire process of rusting.
Now, what's really fascinating, and what this slide shows so well, is how this happens. It's not just one single event. Inside one tiny little water droplet on a piece of iron, the reaction is happening in two different places at the same time. The center of the droplet, where there's less dissolved oxygen, becomes the anode. And the edge of the droplet, which is exposed to more oxygen from the air, becomes the cathode.
Okay, this slide right here shows the two half equations that you absolutely must memorize for your exam. Seriously, tattoo them on your brain. At the anode, the iron atom gets oxidized. You can see it loses 2 electrons to become an iron 2 ion. Meanwhile, over at the cathode, oxygen and water team up to accept those very electrons in a reduction reaction, and they form hydroxide ions.
And here it is. The classic exam trap. So many students fall for this one. You could have a pure iron piece in a room packed with oxygen and it still won't rust. Why? Because you're missing that third crucial ingredient, water. Without water to act as an electrolyte, those ions can't move around and the whole redox reaction just stops. You must have both oxygen and water. Don't forget it.
So, now that we know exactly how rust forms, the next logical question is, how do we stop it? Let's take a look at the methods you'll need to know to build a solid defense against this corrosion.
You can think of these as the 3 main tools in your rust prevention toolkit. The simplest one is just putting up a physical barrier, like paint or grease. A more advanced method is to actually change the iron's nature by alloying it to create something like stainless steel. And then there's the really clever one, my personal favorite, sacrificial protection. Let's zoom in on that one.
All right, let's really focus on the method that trips up the most students but is a huge favorite with SPM examiners, sacrificial protection. I promise, if you can get your head around this concept, you'll be way ahead of the curve.
The concept is actually beautifully simple when you think of it this way. You basically give the iron a bodyguard. This bodyguard is just another metal that's more reactive than iron, like zinc or magnesium. It essentially volunteers to take all the chemical damage so that the iron doesn't have to. Pretty smart, huh?
This slide shows you the play-by-play of the electron flow, which is the crucial part. So instead of the iron atom giving up its electrons and turning into rust, the more reactive zinc steps in and sacrifices its own electrons first. You see, those electrons then flow over to the iron, right where the oxygen and water are waiting. The oxygen and water then react with the zinc's electrons, leaving the iron completely safe and untouched. Imagine it like this. That zinc block is pushing a protective energy shield made of electrons all over the iron hull. And as long as that shield is active, those nasty rust particles, they just can't form on the iron. That is exactly what is happening on a chemical level. The zinc slowly corrodes away, but the ship's hull remains perfectly safe. Okay, theory is one thing, but let's see how this all works in practice. We're going to tackle some real SPM questions now. This is where we learn to put on our examiner hats and think like they do.
Here is a very, very typical exam question.
Notice they don't always give you the actual names of the metals. Instead, they use letters to represent a reactivity series. They do this because they want to see if you understand the underlying principle, not just if you memorized a list.
Okay, don't panic and don't guess. Let's just break it down logically. The first rule is simple. A metal that's more reactive than iron, like W, is going to act as a bodyguard and slow the rusting down. A metal that's less reactive, like Z, will actually make things worse. It'll speed up the rusting. But the key here is what I call the distance principle. The bigger the difference in reactivity between the two metals, the more extreme the effect will be.
So, to get the absolute fastest rusting, you want to pair iron with Z, the one that's furthest away and less reactive. That huge reactivity gap just accelerates the whole process. And to get the slowest rusting, or the best protection, you pair it with W, the most reactive bodyguard you can find. It's all about that distance on the reactivity series.
All right, let's try another one. This one focuses specifically on our bodyguard principle in action. They're basically asking what's really happening in that reaction.
For any multiple choice question, your best friend is the process of elimination. So let's test these options. Does iron release electrons? Absolutely not. That's the whole reason the zinc is there, to stop that from happening. Does oxygen get oxidized? No, oxygen gains electrons, which means it gets reduced. Is zinc less reactive? No way. If it were, this whole bodyguard thing wouldn't work, which leaves only one logical answer.
And there you have it. Zinc releases electrons. That's what it means to be more reactive or more electropositive. It just has a stronger tendency to give away its electrons. The zinc basically corrodes on purpose, all to save the iron.
So let's just wrap up the main idea here. The one thing you should really take away from all this: don't think of rusting as just some random decay. See it for what it is: a predictable flow of electrons, a transfer of energy. And once you understand that flow, you can learn how to redirect it and ultimately how to control it. Just look around you. Your bicycle chain, the front gate of your house, even the stainless steel forks in your kitchen. This chemistry is literally everywhere. So think about it. Which protection method would you choose for each of those things? A simple coat of paint, a specialized alloy, or a sacrificial bodyguard? The right tool always depends on the job. Now, go apply what you've learned and test yourself on the MCQ SPM app. Good luck!